Okay, so next speaker of this afternoon session is Ricardo Ferreira from the let me see, CFIISUC, University of Coimbra, right?
Yeah, that's right.
We'll talk about the domain worlds. Please start.
Yeah. Hi. So hi everyone. Sorry for not being there in person. I really wanted to go. Unfortunately, the embassy didn't give me a time slot for to take care of the visa, so I wasn't able to go. But I hope next time I'm able to join. So thanks organized for the invitation. So it's always a pleasure to talk about these things. So today, the plan of my talk it'd be to talk about the recent progress that has been done in the what regards domain wall networks, which is of course a very old subject, but there has been new developments in many aspects, and I know that some people in the audience are actively working on this subject, so they are familiar with this. And in particular, I will focus on three aspects. Gravitational waves, primordial black holes, and cosmic birefringence. This is work I've been doing with some collaborators, in particular, mostly these two papers from last year with Silvia Gasparotto, Takashi Ramatsu, Ipei Obata, Oriol Pujolas, and also with Alessio Nutari and Fabrizio Rompeneve. So in particular, the phenomenology about the gravitational waves, I will defer this to the talk of Fabrizio Rompeneve, which we'll talk later today. So stay tuned on that. So the outline of the talk is the following. So I will first, I'm not familiar. I don't know if the audience is familiar with the subject. So I will start from the basic features of the domain wall networks, in particular. What are these domain walls? How do they form? And their dynamics. And the remainder of the talk will be about the observational signatures that these networks can have. And so let's get started by the basics of these domain walls. So what are these? How do they form? What are these domain walls? So as you probably know, these in many beyond standard model models, in particular axion physics, but many other examples, multi-Higgs models, Madrons. There are several examples where discrete symmetries appear and are spontaneously broken in the early universe. And this means that so in the early universe there are different minima which are equivalent, like in this picture on the left, and the different regions of the universe that are not in causal contact will independently choose a different minima. And these regions, as the universe expands, at some point they will enter in causal contact, and they will realize that look, we are not in the same minima, and they will find out that because in between them there will be a wall. So there will be a wall, and this wall is basically the field configuration that brings the field from one minima to the other. So what I'm saying is basically just the basics of the Kibble mechanism. And in particular, this wall is characterized by two basic features. So to most purposes, the wall is two-dimensional. So basically, it's two-dimensional sheet across space. And there are two main properties that characterize the wall. So one is the width of the wall. So you see on the bottom left corner. So the black and red denote the two minima, and this is the solution for the wall in field space. So in position space, sorry. So the field goes from the black to the red in a window given by L, where this distance L is basically the inverse of the mass of this scalar field. So it can be very small compared to cosmological scales. So the second property which is relevant is the domain wall tension. So the domain wall tension is the energy per unit area that the wall has, and it's connected with the mass of the field and the difference between the two minima. Okay, but what I've just told you was one wall, but this will happen. This thing that the two minima get enter in causal contact, and there is a wall dividing the two. This will happen in all different places in the universe. So in reality, what we have is a network. It's a network that unites all these walls, and this network has a specific dynamics. So I'll explain briefly, and then I'll show a clip where you can kind of see this happening from a numerical simulation. So on large scales, so basically when these walls have curvatures, very small, very large curvatures, so on curvatures larger than the horizon, these walls are frozen by Hubble friction. So they basically nothing really happens. They are co-moving. On the other hand, on small scales, so once the walls get curvatures comparable with Hubble, so they become subhorizon in some sense, or their typical distance becomes subhorizon, then the tension of the wall overcomes the Hubble friction, and these domain walls start to accelerate. So they accelerate, and they can collide, chop, intersect. So there is dissipation. So there are these two competing effects, one where they are frozen, the other where they dissipate, and this leads the network to the famous attractor regime called the scaling regime, where there is roughly, on average, one wall per horizon at all times, and the typical curvature and distance between walls is always of around r of order 1/h. And so let me show you here a simulation. This simulation was done by Takashi Hiramatsu. And the simulation goes from, goes from the beginning. So basically we see the domain walls forming. So we start from the field. This case is a Z2 symmetry. So the field starts at 0, it has fluctuations, and then it ends up in both minima. And you see that in the beginning, what you see in the picture are the phi equals 0, the surfaces. And in the beginning, it's a mass, but at some point, you see the walls starting to form. They radiate leftovers, so excitations that come from the process of domain wall formation. And at some point, they basically kind of freeze in this, or reach this scaling regime. Okay, so this, I hope you get the picture of how this network looks like. Now, these basic features were known long ago. Well, the numerical simulations are much more recent, but the basic features were long ago, and they were seen as problematic. So historically, the domain wall, we probably all have heard about the domain wall problem, which is the fact that this network has an energy density given by sigma, the domain wall tension, times the characteristical 1 over the characteristical length, so 1 over r, which in this case is h. So sigma h is the energy density of the network. So it goes linearly in h, which means that this network redshifts very slowly. So slower than radiation, slower than matter. And therefore, if the network is there for long enough, it will the network will eventually dominate the universe, and which, as we know, is incompatible with observation. So this was what the domain wall problem stated by Zeldovich already in the 70s. Now, there are two ways to evade this problem, or at least two ways, and which are the following. So one is that discrete symmetry is not exact. So if somehow the domain walls annihilate, so if they do annihilate before dominating the universe, then there is no domain wall problem. And there are several examples of how to do this. So one of the most famous ones is that the symmetry is not exact, as I was saying, and you so basically have that there is an energy gap between the minima. So for some time the network does not, I mean the difference is irrelevant, but at some point the minima will know that they have some energy difference, and because this energy difference will create a force, and this force is able to annihilate the walls. And there is a time for that to happen that is related to this delta V. This is option number one. The second option to evade the domain wall problem is probably the most simple, is that the tension of the walls is simply small enough. So if the tension is small enough, and here small enough means smaller than MEV cube, then the walls basically didn't have time to dominate or to have a significant amount of energy, and therefore therefore there's also not any problem with observations. Okay, so in what I will talk next, I will first discuss mostly this case 2, and then later on, so regarding these birefringes that I will say in a second, and then later on when discussing the gravitational waves and primordial black holes, I'll talk about case 1, so domain walls that annihilate in the early universe. So let's start from this case 2, and this brings me to the first observational feature of these domain wall networks, which is cosmic birefringence. And so let me do some parentheses and start first by discussing what is birefringence and some recent observations that have been done in this regard. Okay, so birefringence, you probably have heard this word in your undergrad courses. So it's basically the rotation, or birefringence will cause the rotation of a photon, of the polarization axis of a photon. So a rotation beta of the polarization axis of the photon when a photon travels through a birefringent medium. And in this regard, what is interesting, what claimed our attention, is the fact that there is observational evidence right now for an isotropic signal in the CMB. So meaning that there is evidence that the CMB photons have been rotated by an amount from recombination. The polarization of the CMB photon has been rotated from recombination until today. So this is analysis has been done by these very nice works by Komatsu and collaborators. In particular, the null hypothesis has been excluded already with high significance, and the current signal seems to be of beta of around 0.3 degrees, 0.34 degrees. So these works, they have done several checks on the systematics and how to extract separate the miscalibrations from the physical effect. So they were very careful on this regard. But I would like to highlight that soon the Atacama and South Pole telescopes will provide independent confirmations, or if they verify, of this signal. So it's something that there will be news soon. So this is on the observational side. But now if we let me move to the theoretical side. And what I would like to stress is that this is a clean case for new physics because there's no obvious astrophysical or late time explanation. So there's nothing really that would give you such an effect, or at least to my knowledge. So it's a clean case for new physics, and in particular, the main ingredients to do this, to generate an isotropic birefringence effect, are the following. So we need to couple two photons, and we need to couple the photons in a parative violating way. This is kind of obvious. So if it is from a scalar field model, so we have something like this phi FF dual term. I'm sorry, my pointer is not working, so I need to guide you with words to the equations. So this is the ingredient number one. So you need to have a source of birefringence. And then you also need a further thing, which is that this field needs to have an excursion. So from recombination to today, it should vary kind of significantly, because the size of the effect, as you see on the second equation at the bottom, is so beta isotropic is proportional to alpha electromagnetic over 4 pi times the difference between the value of phi over f at some time eta, so in particular recombination, minus the value it has today, so eta naught. So the signal is proportional to the amount of field excursion. Now I don't have to probably to convince you that these two ingredients basically call for an axion field explanation of the signal. And in this regard, there has been basically two main ideas. One is using a homogeneous ultralight axion. So basically having a ultralight axion that is a significant component of dark matter or dark energy, and basically this axion permeates all space and is able to make this effect. But the second idea is a bit different, and is connected again to these domain walls, or even axion strings, as I will explain in a second. And basically is the following. So let's go back to the network. So assuming that the network is there until recombination, at least, or perhaps until today, but at least until recombination. So which means that we need to have low tensions of the wall. And we have, so these domain walls are made of this scalar field phi. And each time, if we have this parity violating coupling to photons, each time the photon crosses one domain wall, its polarization axis will be rotated by beta equal to 0.21 C gamma. C gamma is just this coefficient. It should be proportional to the electromagnetic anomaly for those that know this. So it's a coefficient of order 1. It doesn't matter. Times delta phi over f over 2 pi, where delta phi over f is basically the amount of field difference when you cross the wall. So if you look at the plot on the right, when we cross the wall, we have a delta phi, and for axion models, this delta phi is typically of order 2 pi f. And that's the very nice feature of this idea, is that if you put delta phi equal to 2 pi f in the equation for beta, the dependence on f goes away, and you end up with, and 2 pi as well, and you end up with 0.21 C gamma degrees. The situation is similar if instead of walls you have string loops, so cosmic string loops. I'll go back to that in a second. And let me now stress two things. So first, 0.21 is very close to what has been observed, and the number, so I didn't do any magic, so it's what comes from the wall. And second is that the signal is basically independent of the energy density in the scalar field phi. It's independent of the domain wall tension. So even if the field is very subdominant in the universe, we still have this effect. And even f, because the f cancels out, because the f that appears in the axion potential is the same as the one it appears in the coupling to photons, so it cancels out. So it's kind of a robust result. However, what I'm saying here is just for one wall. Of course, if we have a network, we have more than one wall. We have a network, so we need to account for photons that go through kinks but also through anti-kings. So let's look at that. What I'm showing here, and let's look on the plot on the disk on the left, is like an idealized Z2 model, where I'm basically making a projection of the sky. So this is a celestial plot where the radial component of the disk denotes time. So on the edge, we are at recombination. At the center is our current location in the universe. And the angle is basically the angle in the sky. So photons will come. Photons are the yellow arrows, and they will come from the edge of the disk towards the center. Now, the blue and the red denote the domain walls, so denote the two minima. And what you see is that, so for each circle, there is basically as many blue as red regions. And that denotes that the fact that the network is in scaling. So if it's in scaling, there is no preference between two minima, so the blue and the red, and therefore they should be in equal amounts. The domain walls are the transitions between the different colors, so between red and blue. And you can also see that the walls, that some of the walls annihilate. So at some point, some walls disappear as you go in the radial direction in the disk. So at some point, some walls disappear. And the further thing I would like to stress is that we live in the center of the disk, and therefore we need to live either in the blue or in the red. So in some sense, our local universe breaks the symmetry, spontaneously breaks the symmetry. It needs to choose one. I'll come back to this in a second. So on the right, so we use the real data. So we use the data from the numerical simulation of Takashi to make the same plot, this celestial plot. And so it's a bit more rough. As you can see, we were limited by different things. But qualitatively, you see that there is the same amount of red and blue. So there are you see that the plot on the left is representative of what is happening. Now let's try to compute these isotropic birefringence. So what do we need to do? So this isotropic signal is basically what I told you before. So it's 0.21 psi gamma times then the difference of delta phi of phi over f between here I'm showing the isotropic birefringence at the generic time eta. So let's fix eta at recombination. So at recombination, this will be the value of phi over f at recombination, but average because we are looking for the isotropic signal minus the value it has today. So in our local patch, divided by 2 pi. And now let's look at each of the terms. And when we do the average of phi over f at recombination, we basically get 0 because, as I said, even though one wall gives you an effect, when we average over many walls, there are as many blue as red regions. So there will be, so the two things cancel out. Because in one case phi will be positive, let's say, in the other case will be negative, and when you sum over all of them, you get 0. However, there is something left over, which is the local value. Because as I just said, the local value is either red or blue. So it's either positive or negative. And on top of that, it will be of order 2 pi again, because if it's red or blue, then the minimum it's of order the minimum of phi is of order 2 pi f. So again, we end up with the same result. So so you see that even from the network, we end up with something of order 0.21 psi gamma, so very close to the observational signal. Okay, so now how can we use this? How can we distinguish this idea from the others? for example, from the homogeneous axion case. Okay, first, in this case, the birefringence is very anisotropic. So, I mean, the network is clearly not an isotropic distribution. So we expect to have, so if you look at the birefringence at small parts of the sky, we expect to have differences. And so in particular, we can define a two-point function, a power spectrum. And this power spectrum will have, these are the plots on the right, will have two peaks. So first, a peak at recombination, so is the top plot. And why recombination? Because the polarization of the CMB photons is mostly generated at recombination and at reionization. So reionization is the plot on the bottom plot. So this part of reionization was new. The part on recombination, we improve over previous results by making it 3D and making a full sky analysis. By the way, here we are using the results from the numerical simulation. Really. So the second signature is that we can do some tomography. So we can test the annihilation and formation time of the network. For example, if the network forms after recombination, what you expect is that, and let me go back. So you expect that this peak at recombination is not there because those photons that were generated at recombination will not be rotated, but you still expect to see the reionization peak. And okay, and vice versa, and you can do different combinations. In particular, there is so by looking at the reionization scales in the EB power spectrum, and sorry, I didn't say, I should have said it before. So in the CMB, the data that has the information about the birefringes is the EB correlator, because that's the parallax violating signal. It's a parallax violating channel, so it is only non-zero if we have some parallax violating effect. And we have that data, and that's where we extract the observational evidence. But we only have that data at high L. At low L, we still don't have that data, but there are ideas to do it, and that will allow us to make this tomography. And in particular, we could test both the isotropic and the anisotropic birefringence by looking at the EB spectrum at low L, so L is around 10. And the third thing that is interesting, and that these domain walls will give you, besides birefringence, is that if the tension, so for birefringence, the tension is not important. So the signal is not proportional to the tension. However, if the tension is significant, and I'll say in a second what significant means here, you can have gravitational waves from the network, and this stochastic gravitational wave signal, which will be at CMB scales, because the typical size of this network is cosmological if they live until after recombination. And if you look at the plot on the right, so basically we have that I'm showing so different curves. So the red, green, blue are curves that where we vary the annihilation temperature of the network, so from eV to milli electron volt, and also where we vary the abundance of the network at the time of annihilation, from 10 to -5 to 10 to -7. So let me say that so we find that by looking at the numerical at the simulation, we find that the UV slope of the spectrum seems to be smaller than -1, so closer to -1.7, -1.8. So this was a surprise, because the common law is that these main walls have a UV tail of with a slope of -1. So we found something different. So it would be nice to nail down what is precisely this number. And furthermore what we did next was to compare our predictions for the gravitational waves with existing bounds on stochastic gravitational wave signals at CMB scales, and that's the gray regions that I'm showing. So the gray regions are regions that are excluded from, so where the gravitational waves will be too large and incompatible with the CMB data. So by putting the two things together, we derived basically constraints on the maximal domain wall tension. So these are the blue region in this plot. So basically before there was only constraints until annihilation temperatures of 1 eV, but now we are also able to constrain domain walls that live until after recombination. So if they annihilate at recombination, let's say around 1 eV, they can have tensions closer to 100 MeV, and if they live until today, they can have tensions. So we find a maximal allowed tension of order 0.5, 0.6. So this is very close to previous years. So this value 0.5 MeV is close already to the value of Zeldovich. So let me also say that with future CMB data, we will be able to improve this bound by well, a bit less than 1 order of magnitude. Okay, so let me now.
You have
Yes.
9 minutes remaining.
Okay. So let me then briefly. So I might not have time to go to the second part, unfortunately, but so let me just say one last thing about these birefringes, which is that so these domain walls, I mean, they in the axion case, they typically don't come in isolation. They typically come attached to strings. So not always, but in most cases. So you should ask the question. So how are the presence of strings? How is the presence of strings affecting the result? And the answer. So the effects of strings or cosmic strings on birefringence has been studied to some great detail by the papers that I'm showing here. Particular, so there has been recent work by Andrew Long, which I suppose is in the audience, which goes into very much detail in this respect, and basically in what regards the isotropic signal, the effect of the strings is that they tend to wash out the effect at high redshift. So basically, the point is that strings or string loops, they provide kind of an excess of symmetry. So in some sense, the coming from high field values or small or low field values are equivalent, or there is no preference for coming from high or low field values. So so again, at high redshift, this will be there will be a washout when we average over the sky, because to compute the isotropic effect. So what we then argue in our work was that yes, that's true. However, if the network is in scaling, meaning that it lives until today, we expect to have a defect kind of nearby, so at redshift 1 or smaller. And this is a kind of an environmental effect. So basically, there's nothing that can wash out this low redshift defect, because I mean it's very close by, and therefore there will be this leftover. Even if the strings tend to wash out the signal at high redshift, there will be this leftover signal, which is proportional to again 0.21 times this omega over 4 pi, where omega is the angle in the sky that subintends the defect that is closer to us. So we find that to get a significant signal, we probably need the effect to be at redshift of around 0.4. So maybe is not the most probable situation, but it's not unlikely either. So there's still a chance that that is string or string wall networks can make the isotropic signal as big as the observations. And interestingly enough, if this is true, this means that isotropic signal will have a very strong variation at low redshift. So and this might give you further observational tests. Okay, I'll not have time to go to the second part, unfortunately. I hope, yeah, can ask me questions if you are interested in that. So let me stop here so that I have time for questions. Yeah, thank you.
Thank you. But yeah, you have 5 minutes more for questions.
There is
So
5 minutes
if you
more
can
afterwards.
do within
Sorry,
5 minutes, then it's okay.
Okay. Then yes, please. If I'm allowed, then I will really like to go into this part. Okay.
Okay, great.
I'll try to be quick. Part 2. So besides cosmic birefringence, there are other things that we have studied. So basically gravitational waves and primordial black holes. Regarding gravitational waves, I will not say anything because Fabrizio Rompinelli will go in great detail on these aspects. So please take a look at his talk. So I'll jump to the primordial black holes. So what's the point? So I'm assuming now that the network. Let's not talk about specific times now, but let's just consider a network that lives until some time, and then it annihilates because of this difference of because the symmetry is not exact, and there is a bias. So there is this energy gap between minima. So before annihilation, the network is composed of, as you saw in the picture, and as I argue, of Hubble-sized domains, roughly, of each vacua. So each vacua is equally distributed because there's no preference between from one vacua to the other. In particular, for a Z2 symmetry, you could very roughly you could have this picture of you have Hubble-sized domains of. So here the two minima are denoted by green and blue. And you could have this picture that you basically have double-sized domains, some with color blue, some with color green, sorry. And they are equally populated. And the probability because the probability to have blue or red is 1/2. Now, there are regions, they are rare, but there are regions in the universe where you could have a super horizon size with the same color. They are rare because, so if you measure that each Hubble patch, so for example, look at the figure on the right. To have a region that is bigger than Hubble and all blue, you need to have the probability to have this will be 1/2 times 1/2 times 1/2 times 1/2. And therefore, the bigger it is, the more improbable it becomes. However, these regions are important because after annihilation, everything that is Hubble size goes away. The network is destroyed. There is nothing left over. But the only thing which will remain are these big structures that are not able to be destroyed. And this is what we call these false vacuum pockets. Because these are pockets that have inside this vacuum energy, basically the difference in energy between the two minima. And they have a radius larger than 1 over the Hubble at the annihilation time. And as the universe then expands, at some point they will re-enter the horizon and collapse. Now you can ask the question of what's their distribution, and the distribution is for a Z2 symmetry basically 1/2 to the power the number of Hubble-sized domains that fit inside that radius. So having a probability to find a domain wall of radius RDW is basically 1/2 to the power the volume of the sphere. So here I'm making a spherical symmetry approximation for all the walls. 1/2 to the power the volume of a sphere of radius RDW over the value of the Hubble at the time of annihilation. So it's 1/2 to the power RDW H annihilation cube. I'm reading the equation. And then you can ask the question, so, and what's then the fraction of false vacuum, fraction of the volume that is in these false vacuum pockets? And what we find after solving the number go-to equations, because the domain walls are not static, they evolve, RDW is a function of time, we find the following. We find 1/2 to the power minus 1.8 eta over eta annihilation to the power cube. So let me say that this is, of course, very sensitive to the number 1.8. 1.8 is taken from a semi-analytical approach. However, we do find agreement with between this semi-analytical and the numerical result. And given the big power that we are talking here, this is so gives us confidence that we are doing the right thing. And sorry for being quick, but just to wrap up this story, the relevance of these false vacuum pockets is because they are so you have vacuum energy inside. So this vacuum energy does not dilute with expansion. So if at some point the false vacuum pocket that enters the horizon satisfies the condition delta V equal to 3h squared mp squared, because h is decreasing, and that pocket, the pocket that enters the horizon at that time, has a Schwarzschild radius equal to the horizon, of the size of the horizon. And basically we satisfy the Hooke conjecture, and this will be a black hole. And so this is the mechanism of forming black holes. There might be black holes that form even earlier, but those are much harder to account, and yeah, and we have not done that. So to wrap up, basically, and I hope then Fabrice will have more time to discuss this. So we have this mechanism of PBH formation from the leftovers of the domain wall network. So these these rare false vacuum pockets, and this is in agreement. I mean, there are some hints of gravitational waves at pulsar timing arrays that could be explained from domain walls, these PBH constraints are the PBH that are formed from this mechanism are compatible with these observations, and might be even detectable in the near future. So I'll wrap up now with the conclusions, and I'll leave the conclusions for you to read over there. So thank you for your attention.
Thank you for interesting talk. Our session is open for question.
Hey, thanks for the talk. I was wondering, you had this condition delta V is equal to m squared h squared?
Yes. Sorry, I don't know. Yeah, I'll give me a second. Yeah, here. Yeah. So basically, this condition, this is a generic condition. I'm just saying this sets a time. It's the time when delta V, so the the time when the overdensity is of order 1, basically. Sorry, I'm not hearing you.
Yeah, sorry.
So from the beginning, I didn't hear anything. So
okay, I think I understand. In principle, you just want to have delta equal to 1, such that yeah, you hit the threshold for PBH production. But in your case, does this not mean that this pocket inflates?
Yeah, this is I didn't want to go into that. This is the picture on the right, as has been discussed by Garrigue and Vilenking long ago, no, to 2016. So what happens is that on the inside, it inflates.
But from outside,
on the
observer,
on
it
the
looks
out,
like
but
okay.
on the outside, it collapses, and in
Looks
particular,
like a black hole. Yeah.
it's a baby universe because when it evaporates, it you have something that disconnects from our universe. But that's okay. You can go to their paper.
Yeah.
It's an interesting. Yeah, it's interesting.
Okay. Yeah. Thanks.
Any other questions? No? Let me clarify the situation. In order to have this two-manual annihilation, you always need the bias, right?
There are other. So in what we study, we use the bias. There are other ways to annihilate the network. So, for example, if the tension goes away, so if you have some symmetry restoration, for example, you can also annihilate the network. Yeah, there are more ways. The bias is the most commonly used. Yeah.
In order to have the symmetry restoration, then you have to add some extra structure for your theory, right?
Yeah. Yeah, we did. That's right. So we didn't go into the symmetry restoration case. So we just focus on the bias. Yeah. Each case requires an additional layer on top of the discrete symmetry, of course.
Okay, thank you. Any other question? Last chance? No more? Okay, then let's thank Ricardo again for his interesting talk.
Thank you, everyone.
Thank you, Ricardo. Bye-bye.